let's get going. So like I said, I'm going to just, I threw some slides together. I'm going to talk a little bit about, here's the title, Mechanism Design, which is an economics terminology in some notion of decentralized machine learning. So this is an academic slide. I really think a lot of this is driven from industry, and really we should reflect kind of what industry needs to achieve, but still academics need to reflect that. And I kind of like this slide, which is that there's an emerging engineering discipline, whatever you want to call it. It's not really AI, but it's, large scale Internet of Things, data flows, humans involved in various loops and so on, whatever you want to call it. And I think that there are three foundational disciplines. I mean, there's many allied disciplines, but statistics, computer science, and economics. And most people I talk to who work in this general field work in kind of two of those, and they think they're a bridge. And they really, I want to emphasize that we should kind of be in the middle of this triad. And in fact, historically, there have been lots of bridges between pairwise interactions. Computer science meets economics. That's called algorithmic game theory. And so if you don't know about that, there's textbooks on that. There's a conference called the EC conference, and it's a real thing. It's mostly algorithms focused on, incentives, meets incentives. There's very little machine learning there, very little statistics, very little uncertainty, not entirely absent, but and only recently has there become more of it. Similarly, statistics meets computer science, that really is machine learning. In fact, I think machine learning is mainly statistics, but with computational overtones. And so, that's been a very healthy. And of course, statistics meets economics, that's econometrics. Econometrics, however, is just mainly measuring the economy. That's what econometricians do, and a little bit of causal inference. Right? They're very much not out computer scientists. Econometricians, maybe know how to invert a matrix, and that's sort of not the extent of it. The machine learning people are mostly not knowledge about economics. Okay, not everybody. This is true. But anyway, if you go into industry and sit at the table solving a real world problem like at Amazon or Alibaba or something like that, you'll find people from all three disciplines around the table. And there's also often operations research, control theory, and applied math and so on, and allied disciplines. But there's these three perspectives are very much present. Okay, and also I just want to say as an academic, this is nothing new. Blackwell, von Neumann, Arrowwald, et cetera, were already blending all three of these, and somehow their spirit kind of disappeared over the years. Things kind of got balkanized much more. People focused on subsets of the problems, and I think what's happening now is we're bringing it all back together. And we realize we don't have quite the right tools, right? So we could use our classical convergence analyses and algorithm study and large numbers and all that, and it's not quite right. It's not really solving the full problem. So I think it's a really exciting time. Machine learning is more my kind of home discipline. It has become such a hugely hyped, but impactful area, but mostly focused on just pattern recognition. When you say machine learning, you mean large amounts of data and then either supervised or unsupervised, predictions and making good predictions. And there's some people in machine learning that sort of argue that's all there is. If you make really good predictions, then you're done. I couldn't disagree more. Decision making is not just about predicting things, it's about kind of considering what if experiments, having a dialogue, considering other options, considering the interactions of yourself with other decision makers, considering things over time, how they'll interact, and all the things that really humans do very well. As we think of this as more like reasoning, but that's what's missing in machine learning. And so this decision-making side is, is emerging, and it's not just imitating human decision-making. That's the thing of its own. It's really economics decision-making. When you have large-scale markets, that's kind of a decision-making entity, mostly done non-adaptively. Most market mechanisms are not adaptive, but as soon as there's data flows that could be all adaptive, it's much more interesting. And that's really what's emerging in this era, as far as I'm concerned. Okay, so just to say, I'm not gonna go through the slide, but decisions is much more than just thresholding things. And in particular, when you start to get scarcity and competition and asynchronous decisions and decisions over, decades, lots of hard decisions are made over decades. It becomes a much richer topic than it seems to be in the current machine learning literature. And I kind of use recommendation systems as a little thought experiment for a lot of the work I've been doing, because it's decision making and it's data and it's social. Okay, so it brings together all three, even though it's not everything. It's a nice little kind of thought experiment domain. So you know what it is, but it's mostly been treated as just a pure prediction problem. If you can predict what users want, you're done. And of course, that's just not true. If you start predicting what movies people will like, then you can serve, hundreds of thousands of people, whatever movie they want. And if everyone likes the same movie or you serve the same movie to everyone, that's not a problem. And same thing with books, if you recommend books to people. But if you start recommending things like real world goods, restaurants, you can't recommend the same restaurant to everyone, even though everyone looks like they like it. It's a great restaurant and everyone loves it. You can't recommend it to everybody. You create congestion, right? And you don't solve that problem just by load balancing, quote unquote, deciding that 10 people are going to go there. I'm going to choose which 10. Okay? Because you don't know how to choose which 10. You don't even know what they prefer. They may not really want to go there, or they might really want to go there. That's a utility. So you got to respect their utilities and try to bring that in. Now we're starting to talk about markets and economics language. Same thing with recommending things like streets and drivers. We've already seen congestion being created by recommendations. Sending everybody down the street that seems to be the fastest automatically makes that street no longer the fastest. And people have started to realize that, but they don't have good solutions to it. They think of it as a load balancing problem. I'm going to choose because I know something about people, or I've been on I know their browsing history. Therefore, I know which route they really prefer. That's kind of the mindset often of Silicon Valley, very top down, gather lots of data, make it a prediction problem. It's not a prediction problem. It's a market problem. It's a auction problem, really. It's a valuation problem. Okay, so this is the alternative to predictive-oriented machine learning, which is that machine learning should really be about structuring markets and two-way markets, multi-way markets between consumers and producers and other entities, brands and so on. Drivers on one side, street segments on the other, diners on one side, restaurants on the other. And so it's not just classical game theory and mechanism design. That's a field of its own, Nobel Prizes and so on. It's all of that in adaptive, all of that with data. Because in economics, again, econometrics would gather data to measure the economy, mostly from macroeconomics. They rarely gather data to build a mechanism on online, learn about something and have the mechanism proceed. I like this slide. This is my real world involvement. I've been involved in a company called United Masters, which is doing this at really large scale. And I think it's fair to say at this point, it's revolutionizing the music industry. There are over 2 million musicians now signed on to this company called United Masters in the United States. And it's created with data, a multi-way market between people who make music, which are usually 16 to 20-year-olds, people who listen to music, which are mostly 16 to 20-year-olds, and brands like the National Basketball Association, which have a lot of money and are interested in all these kind of people. And so now if you go to the National Basketball Association and you watch a clip, there'll be a clip and there'll be music behind it. And that music is coming from United Masters musicians. And every time you watch a clip, the money to pay for that from the NBA is going to the musician. So that's a real market. And now there's like about 2 million young people in the United States who are really good at making music or have a salary. Right, so this is brand new. Of course, the music industry hates it, but they're dying. And this kind of thing is taking over. So, the creator economy broadly. Okay, so here's just a little statement of what federated learning could be if we just add some of this economics kind of language. So the broad problem is that we've got resources that are distributed. We don't have data all in one place. That's kind of the classical federated learning problem. Let's bring the data all into one place somehow, or not bring it all in one place, but let's bring the gradients in one place and then aggregate them. But in general, what's happening is that you have some data, I have some data, and we don't want to just give the data anyway. We own the data, and we want to get some value out of it. And we have our own strategic interests in being involved in some consortium where resources are being shared for some purpose. Right? So the nodes of your network should not just be sources or sinks, they should be strategic agents. And strategic means that they both have an interest in some outcome, but also they're going to play games with you. Okay, they may lie or cheat or steal to get the value that they want out of it, but they don't want to do that. They really want to be in a good economy where they don't have to lie or cheat or steal. Right? So they have valuations of their private data, and valuation is a hard term. In fact, half the problem is going to be how do you value things like data going forward in the context of other people's data. And machine learning will play a big role there because valuation of data is not just an abstract, this data is worth a lot, this data is not. It's for predictive purposes. You can bring in the prediction ideas. If you can predict well with this data plus this data, it's sort of a Shapley value kind of way of thinking that gives you some indication this is actually valuable data. And you could value it in that way, and that could be part of the economy that you start to build. All right, so given all that setup, distributed data and uncertainty about what, or lack of information, okay, there's not full information everywhere. How do I get a task accomplished? So I'm some principal, and it may be Google wanting to build a language model, but let's not think so narrowly. It's maybe some task like build a healthcare system. And I'd like to have a healthy healthcare system where people are not dying. So if I want to do that, accomplish that task, and there are people who don't want to just give me the data for that, and there's all kinds of constraints, how do I build that system? How do I build the incentives into that system so that things do flow and I get things done? And I'm going to obviously have some inefficiencies because I can't just have everything centralized and everything. And so can I quantify that? And can I mitigate all of that? All right, so that's all economics language in contact with statistics language. Here's for more of this is a slide I've had for several years now, but this just gives a sense of some of the intellectual problems that arise when you start to do this kind of program. And so in particular, optima are something we really know and love in machine learning. We know how to arrive at optimal rates. We know, dimension dependence. We kind of started to nail that, stochastic, non-stochastic, and so on. And several of you in the audience have been doing all that. But in these economics kind of problems, we don't really care so much about optima. We care about equilibria. And we care about how fast you approach equilibria. Do you approach equilibria at all, or do you not converge? And there are new issues that arise there. And then moreover, we don't just want the endpoints, we want the dynamics, because the world is changing. And you can't just say, I'm going to go to an equilibrium and I'm done. We want these systems to be adaptive over time. And then I've already kind of alluded to some of these things about multi-way markets when you have recommendations and data informing the recommendations. You need to do better uncertainty quantification. That's kind of a side issue, but it's just something I continue to push as a statistician. Machine learning people do not think enough about uncertainty quantification. If you're going to start to do this in the economics context, you just have to do it better. And there are definitely a lot of progress on that. And then mechanism design. I will just say a couple of words about contracts in my last few minutes here. And then Praneeth is going to also pick up on that. How many of you already know about contract theory? Just curious how much background you have. Yeah, so 3 of you do. So I'm going to tell you about it. It's really interesting. How many of you know about auction theory? So everybody knows about that. It's kind of funny. So just briefly, game theory is the mathematics underlying microeconomics. It's kind of the forward direction. The inverse problem of game theory is mechanism design, finding a game that gives you the outcome you desire. And there's 2 main branches of mechanism design. There's auction theory and contract theory. Auctions have been widely used because of ads, and everyone knows it for that reason. But contracts are just as widely used in the real world economy, just again, not adaptively. So there's a huge opportunity to do it adaptively. And I think it's really important for this collaborative or federated learning problem. So let me just say a little about a project we did last year that kind of get this started with colleagues Stephen and Jake at Berkeley and Michael at Stanford. Contract theory is often called the theory of incentives. It's an asymmetric version of economics. A lot of economics is kind of these crossing curves, and it's all symmetric. Contract theory is explicitly asymmetric. So you have a principal who knows something, an agent who knows something different, and the principal often want to get the agent to act, even though the principal can't just tell the agent to act. All right, so you all know about this. You were just on the airline recently, and you know that there are economy fares and business class fares, right? And it's kind of obvious in some sense why there are, but it's not just in the airline industry, it's everywhere. And so, if you think about it for a little bit, it's kind of interesting. And in fact, there's a mathematical theory of this. And just the short thing is that I have an airline and I set a single price for everyone, 100 euros. There could have been people who were willing to pay 500 euros because, they're richer or they're in a hurry or they just really want to go on this flight for some reason. And I lost all that possible income. I could have, if I had a higher price, I would have gotten much more income, right? But if I set a higher price, I will get them, but I'll lose all the poorer people who just aren't going to pay that kind of fare. And so now my airplane is never full. Right? So if instead I say, oh, I see you were willing to pay more, I'm going to make you pay more. And if you're willing to pay less, I'll make you pay less. That's called price discrimination. And first of all, it's kind of impossible to do it. People will fake their identity and it's illegal. So what contract theory does is it sets up called second or third tier price discrimination. And you all know what it is. So we offer not just a single price, we offer a menu of prices and accompanying with each price a service. Price, service, it's a menu of options, okay? And you know what it is. So now how do you set that menu and how do you set that price is critical. If you set it wrong, this thing will all collapse. All the rich people will pretend to be poor or vice versa. All right, and so you have to set it in the right way. And there's various crossing curves to determine this, and various derivatives have to be, Right, but what it works out then is, of course, that, if I offer people a little more of a service, that they're first in the line, they get a little glass of red wine free, that's enough for them to pay hundreds of dollars more. And of course, it's ridiculous, but it works. And so the rich people come in and say, you have to ask me if I'm rich. I see that option. I'm going to select that option. You've kind of informed people a little bit about your own private valuation without running an auction by the choice you made. And that already leads to a Bayesian way of thinking. I can now, 5 minutes? Perfect. I already know that I can start to extract information by running a set of options, and I can start to do Bayesian inference on that information. I could do that over time, and I can actually start to build up a posterior. So something is leaked to me. All right, so anyway, someone picks that option. Someone else comes in and says, no, I don't care about the stupid glass of wine, and I don't need to be first in line. I'd much rather pay, 50 euros. And so a huge flock of people do that, and the airline is full, and you can now compute. The social welfare is higher. It's optimized. Okay, so that's a field of its own. All right. Here's a real world application of this that's not just pure contract theory. So the FDA does clinical trials every year. It costs tens of millions of dollars to run clinical trials. You all know about this, right? The vaccines, for example. And it's exactly the situation. The FDA has partial knowledge. They're testing drugs, but the drug candidates are coming from drug companies, and drug companies have a little more knowledge about whether the candidate drug is a good one or not. They don't know for sure because they only did an internal test with a few people. They can't spend $10 million to do a real test, but they did an internal test, or maybe they know they put their best engineers on this, or they may know something. But the FDA can't just come to them and say, tell me what you know about your drug. They're not going to, they're going to lie. All right, so instead, the drug companies are incentivized to throw as many drugs at the FDA as possible, because the FDA is doing a statistical test. Okay? It's not just an outcome. They're going to run a statistical test, and there's a possibility of false positives and false negatives. And if I'm a drug company and I even know my drug is not any good, it's not maybe bad, but it's not good. I give it to the FDA. There's a false positive. I can still make a huge amount of money, right? And so I'm incentivized to do that. People do that all the time, right? So here's just some numbers of kinds of tens of millions of dollars that are spent on testing drugs, many of which are bad drugs. All right, so how do you do this? Well, statisticians came in and they said, okay, we're going to set up an optimal test, a name and person test, false positive rate of 0.05, false negative rate of 0.2. And, they set that up and, found the boundary and all that. And now you can ask, is that a good statistical protocol? Well, in classical statistics, it's optimal. Yes, it's good. But in this setting, it's not economically optimal. It's inefficient economically. So case one, suppose that it takes $20 million to run the trial. If you were approved, let's suppose you make $200 million. All right, and so now you can do a little simple calculation. Given that the drug is not good, theta equals 0. Okay, that's under the null hypothesis. We don't know if that's true or not, but let's do the calculation as if we knew. Then the expected profit is minus 10 million. So I can do that calculation, and the FDA can do that calculation. And we both realize it's not in my advantage to send the drug to the FDA. I'm going to lose money on that, so I'm not going to do it. On the other hand, the same exact statistical test can be run in case two, where it still costs 20 million to run it, but if it's approved, it's 2 billion. So maybe it's like, ibuprofen or something. All right, now you do the same calculation, you realize the expected profit, even if your drug is not any good, is actually 80 million. So you're definitely incentivized to send the drug, as many candidates as you can to the FDA. All right. So how do you deal with this? Okay, and the answer is, of course, you set up a contract. And so Praneeth is going to get into this more. He saw how to start to apply this to federated learning. And I think that concrete example will be the best way to really get introduced to this. But just to say, statistical contract theory, it's our terminology, but it's a contract where an agent comes in, they either opt into the contract or not, they pay a certain amount, and then they choose a payout function like business class or economy class from a menu of options. And the menu has got a payment and it has an outcome that depends on a random variable Z, which is sampled from the distribution depending on theta, which is the true theta, which no one knows. Okay, so that's statistical and contract theory to coming together. And then the agent receives a payoff that depends only on the random variable, but the principal has to get the utility that depends on the random variable and the true theta. Because if the FDA approves a drug and it's not any good, they'll pay for that later in reputation or whatever, or time or effort. Okay, so anyway, that is a setup, and now the whole problem becomes designing this menu. And can you give me guidance for designing that? And let me just tell you, we have a paper on this now, you can read about that. There's a beautiful mathematical result, which is we have a characterization of menus, optimal menus. And they are in one-to-one correspondence with something called E-values in statistics. So if you don't know about E-values, you should probably learn, it's a brand new kind of idea. Well, it's not completely brand new, but P-values everyone knows about, they're tail probabilities under the null hypothesis. E-values are random variables under the null hypothesis that have an expectation less than or equal to 1. So it's a class of measurable functions. And it turns out they're in one-to-one correspondence with optimal contracts. So contract theory and Neyman-Pearson theory, suitably understood, actually really do mesh well. And so anyway, the paper will get into E-values and show you what they are and start to show you how you can now design contracts that do the statistical testing. And we're actually going to talk to the FDA and start to do things like this. But let me just stop there. I am going to, Pranith will pick us up later. I think contract theory is just fantastic. There's books on this. Lafont and Marty Moore is a classical one from about 30 years ago. If you haven't learned about this, that book is a wonderful read. I highly recommend it. So I'm going to stop there. Any quick questions before we move on?
This is really great, and yeah, I was not completely aware of all this theory, so it's very enlightening as a talk. And just when we talk about so implementing this new set of this new way of working into the machine learning domain, so for targeted domains, for example, healthcare, or I don't know.
Yeah.
Often the incentive and also the utility is not really well defined, and even the improvement of the accuracy of an algorithm with respect to a data set, it's very difficult to robustly assess, because we know that generalization and also what we see in challenges that improving the quality of a model on a given task, on a given data set, doesn't mean that the model is necessarily good. And so how do we deal with how do we actually make it such a way that this theory, which is complete and very nice, meets actually real world constraints and complexity?
Yeah, so thanks for asking that question. That's a great question to ask. I mean, first of all, the short answer really is that this is a several decade project. Okay. And what you're asking is, you're just saying, here are the real challenges. They're not gotchas. Okay. And statisticians already 100 years ago were facing the same issues when statistics kind of got started. It's all this messy stuff. What's a probability? No one really knows. What's long-term averages? What's a reasonable loss? And in field after field, eventually, good best practices emerged, and particular uncertainty quantification. So some of the things you were saying was that the classical machine learning problem is that I don't know, I get an answer and I don't know how good an answer it is. Well, already if you do, say, conformal prediction or whatever, you get some notion of confidence interval around that. And the confidence intervals, of course, it also depends on a little bit of the model, right? But there are good confidence interval methods, right? And if you don't do that, you're really not being a good engineer. Okay. And so part of the secret sauce here is taking a theory which has a lot of probabilities in it, and a lot of valuations and a lot of structure, right? But a lot of things are assumed known. Now, if you put data in, you don't just plug it in and hope it's good. You plug it in, you put uncertainty quantification, and you say, if I have this amount of uncertainty, how bad will the overall economic efficiency be? What about my robustness? So conformal, I want to just mention, if you haven't seen this recently, conformal prediction is a way to give you confidence intervals that are distribution free and model free. So it's really a holy grail.